Very exciting introduction of Jeff. And so welcome everyone to PL Talk. This is our weekly live stream. I'm Jean and this is Hami. And we have a special guest today, Jeff Bezanson, who is the co-creator of Julia. And just a little bit about PL Talk. This came about because Hongi is a security engineer. I am building a product and I met Hongi and he just started asking me questions about programming languages and we just started talking about it more. And then when Hongi switched jobs last time, I was like, hey Hongi, do you want to do a Twitch stream? And I didn't expect him to say yes, but he did. And so here we are. That's all we'll say about us. Hongi works at Figma. I have this company called Akita. You can look up both on the internet. But now on to Jeff, our special guest. Jeff Bezanson co-created Julia. We'll let him say which year. But he's a very special guest to me in some ways because I've known him since 2005. He was my TA and he used to sit next to me in office hours and tell me about this language he was working on. And he would tell me how much better it was than MATLAB. And I didn't know anything about anything at the time, but I was like, well, why isn't this guy the most famous guy in the entire world? It sounds like this language is really good. And Jeff has had this extremely interesting journey over the last decade of Julia becoming one of the hottest new languages that exist today and becoming wildly popular, which is everything I had thought Jeff deserved when he was my TA. And also some fun facts are, first Jeff was my TA, then we were TAs together, then I was his TA. And as part of his journey, I think maybe he'll cover that. If not, I'll chime in. But I think it'd actually be really interesting for Hongi to give his intro of Jeff because like the Julia from the outside intro is something I'm very curious about.
Oh, I was gonna say I know almost nothing about Julia other than I have heard of it as a hot new language that people want to learn, and yeah, I feel like for me it's like the Haskell, like oh if I don't learn it I feel like I'm missing out. I should
you are
totally
missing out,
on that
yeah.
trade.
Yeah, and how Jeff came from obscurity, no offense, Jeff, to
everyone
this.
does, right?
Yeah, is a super interesting story. So, yeah, Jeff, do you want to? So, I guess the bio points we should cover about Jeff are he co-created Julia. He's the founder and CEO of Julia Computing,
or CTO.
CTO of Julia Computing. Yeah, he's full-time on Julia now. That was his dream when I first met him, and he has fully achieved that dream. So it's very, very exciting.
All right. Well, hi, Jean. Hi, Hongi. Thank you for having me on here. I'm pretty excited about this. I think this will be fun. So yeah, but the whole backstory. So my high school physics teacher got me a summer job at a MRI research lab at Cornell Medical School in New York.
As high school teachers are wont to do.
And, yeah, I mean, she knew that I could program, and they're like, hey, they could use a programmer to help them program stuff. You know, you could do it, right? Yeah, I think, you know, so I learned so much stuff there. That's where I learned what a Fourier transform is, which was pretty cool. And yeah, I was helping, you know, writing programs for them to do like kind of image analysis and image algebra kinds of operations. I did a lot of GUIs actually. They needed a lot of like user interfaces because they're writing programs that like manipulate images, and you really need like, you know, to be able to click on stuff and look at stuff. So there was a lot of that, but that's when we were using a lot of C, so a little bit of MATLAB, you know, and I just started thinking there's something about this. There's not a really good way to write these programs. You know, it just really started bothering me. Like I felt like there's not a good way to do all this stuff. Like we don't have good abstractions. Everything is always too low level or too slow, or it just was not a very productive. It didn't feel productive. You're not happy while you're working on this stuff the way you should be. And meanwhile, in a parallel universe, there was this other guy, Stefan Karpinsky, who I hadn't met yet, but he was doing not the same kind of thing, but he was working as a data scientist, where he basically made the same kinds of observations because he's doing linear algebra, doing like recommendation engine kind of stuff. So there's lots of math and statistics, and then he has to operationalize it, and put it into a whole web stack. And it's just a lot of messing with lots of different languages and tools, and it just, it doesn't seem to work very well. And so he also started thinking about, what would be a better way to do this. And then years went by. For my part, at that point, I kind of started like playing with programming languages on the side, and it's something that a lot of people do, right? Like making a programming language is not actually that hard, right? Like you learn how to write a parser, and then you parse things, then you write a little interpreter, and it's not really that hard to do. It's actually kind of, there are even like elementary programming books, like Intro to Programming, where you write a parser, for example, right? Like it's not really that hard. So I wasn't doing it at a very high level. I was just kind of, just playing with that kind of stuff. I just thought it was really fun to, be making a language. And then at some point, when we were TAs in one of the Intro CS courses at Harvard, I'd gotten to some point where I thought maybe I had some worthwhile ideas, and I remember trying to pitch some of it to Radhika, one of the professors. I just a little bit, tried to convince her that I had, maybe there was something worthwhile to do here, but I probably didn't really have anything. I don't think
Radhika was the professor we TA'd for together.
Yeah. I don't think I really had anything, so I couldn't really impress her. But
yeah, to put things into context, this is like 2005-ish. I think that's what Gene said.
Yeah.
So like, what do you think was the state of the art at the time in terms of the programming languages you were looking for to solve the problems you were particularly dealing with? Was it like earlier you mentioned, I was writing code in C and MATLAB mostly for this MRI lab. Was that still at the time? I don't think was R a thing? I don't think all of the NumPy, those languages or those frameworks hadn't come out yet either, right?
Yeah, that was an interesting time because it was just at the point where like Python, NumPy, and R kind of both started taking off like a rocket. They were both existed and used pretty widely already at that point, but they weren't, household words, so to speak.
Yeah, something really interesting was in one of my tweets announcing this talk, I said, Jeff started out working on this MATLAB competitor, and someone was like, no one uses MATLAB anymore. But I remember at the time, MATLAB was the language. We all learned it. I was also programming in MATLAB in my summer internship.
Yes.
Yeah.
Oh yeah. Yep.
Same. So back then, it would have been extremely strange to teach Python in a college.
Yeah, it was a scandal.
That would have been super out there to even especially to do an engineering course, say, in Python instead of MATLAB, which now people would do, and that wouldn't be crazy. Back then, it would have been crazy.
Yeah.
You could have done it, I think, but it would have been considered crazy.
Yeah, and Jeff, so you talked about how Stefan was in this parallel universe thinking the same thoughts. How did you hook up together with Stefan? That came out weird. How did you guys start
where the parallel universes met is since I was interested in this stuff, I found this job listing for a company, Interactive Supercomputing, that made basically a huge parallel MATLAB extension. And I was like, oh, this is cool. This is the stuff I kind of know about. It's a little bit programming languagey in this sort of space. I actually think I know something about this. So I applied to that, and they hired me. And I met this guy, Viral, there.
That's how you met Viral. I was wondering.
Yeah, and he, because he did a lot of sparse linear algebra and high performance computing stuff. And he was at UCSB with Stefan. And anytime he was around the office, I would kind of talk his ear off about, my ideas for other languages. And he said, you sound exactly like this guy, Stefan, that I know. You guys should talk.
And then Viral also got caught up in it. So what was the timeline for all of this? When did you start thinking about it? When did you meet Viral and Stefan? When did you guys actually start working on this?
So I think I met Viral probably 2007 or 2008.
Oh my gosh, this was after.
Yeah.
After you, so I remember, from 2005, we talked about this all the time.
yeah, this is, I like put this down and picked it back up and then put it down again and did other things for just like years and years. Like I'm very slow,
Yeah, because I like what I remember is for like most of the later 2000s and the early 2010s, Jeff was like, working. He was like a musician where, he was like working these jobs, working in Julia on the side. And like, I wasn't really sure how Stefan or Viral were involved, but like, I would run into Jeff like somewhere in a hallway and be like, hey, Jeff, how's Julia going? And he's like, oh, I'm working here. I don't have as much time for it anymore, but, it's still going. And then one day he showed up in the PhD program where I was at, and he's like, I decided this is how I'm going to work on Julia full time. But I don't know, Jeff, if you want to talk a little bit about like that path, because it was super interesting to me. It was like, this is the most dedication I've seen from anyone working on a programming language.
Yeah, it's the 20-year plan, just 20 years later. But so interactive supercomputing. So one of the co-founders of that company was Alan Edelman from MIT.
It's all coming together.
So I met him there.
Yeah.
Yeah, so that's where I met him as well. And so that company was eventually acquired by Microsoft. And Viral and I were the only two people at the company who didn't want to go to Microsoft.
I see. Okay, that makes a lot of sense. And so were you working on Julia at the time you were working at interactive supercomputing?
Not really. So until this point, Julia, as anyone knows it today, did not exist yet.
Oh.
So
But you kept telling me that you were doing things that were faster than MATLAB. What was that?
That was, so there were various other languages, I was like experimenting with, trying to make they would not be recognizable, I don't think.
Well, you called them Julia, no?
I may have called one of them Julia. I had some other names for a while.
That's true, yeah. So
did those ideas live on in Julia? Like, would you say that
name was the best name?
Yeah, I hear that's why Hongi has the Julia fractal in his background.
Oh yes, so I heard that Julia is named after the Julia fractal, which is why it's my background today. But I also heard a different story from Jeff.
Do we have a slide for that?
I don't think. Oh, we can pull it up.
Yeah.
Or Gene can pull it up. You're a master at this.
So I'll just finish the story. So so Viral kind of put the team together, and he said, you should pursue this thing you're always telling me about. So why don't you go talk to Alan and see if he can bring you to MIT, which he could. And then we all just, Stefan and Viral and Alan and I just started brainstorming away and getting started on this. And actually at that point, I started from zero. I threw out absolutely everything I'd done before that point. And so we started completely from the beginning at that point.
Ow.
Yes, there we go. There's the visual.
So yeah, what do people in the audience think? Is Julia named after the Julia fractal or the other Julia? You can tell us in the chat. Yeah, I guess we can just resolve this at the end. We can just have drama until then. People please chat about it.
I don't know. The truth comes out.
Yeah. But yeah, this is a super interesting story to me, Jeff, because I never really got this full story like this. I just kept running into Jeff, and then he showed up in the PhD program, and I was like, this is the most epic, devoted language design person I have ever seen in my entire life, which, granted had not been that long at that point, because this was many years ago. But yeah, it was pretty incredible.
Yeah, you have to be a little bit nuts, and from the time you start trying to design a language, it might be 10 or 15 years. So you have to be patient.
Was there something in particular that made you think like, hey, I should not worry about all the things that I've tried before. It's time to start from scratch. Was there like a particular reason that you sort of came to that conclusion? Was that just like a gradual thing over time where you realized some of these ideas weren't working the way you expected?
I had just learned a lot. So I learned a large amount at interactive supercomputing. For example, from Perry Husbands, who I worked with there. He knows quite a bit about compilers and HPC. Learned a ton from him. Learned a lot about the whole linear algebra world from Alan.
So
I just felt at that point I had totally different ideas of what to do.
So I'm curious now, like what was the problem statement when you started? What was Julia like V0? and like
Yeah.
how, well, yeah.
So I would say, you know, the four of us, there are a couple of problems that we're kind of interested in that the way I would phrase them is that one is the pseudocode problem, which is, you know, you want some way that you can write a program like you would in a paper or on a whiteboard as simply as possible, like pseudocode, but then actually be able to run that, right? You should be able to just lift something out of a paper, present it as simply and elegantly as possible, and then just run it immediately, ideally. Maybe you have to do 2 other steps, but you know, why can't we
Yeah,
do
because
that?
I remember I had this question for you at the time because I was like, but Jeff, MATLAB is pretty close to that, isn't it? What's wrong with MATLAB?
Yeah, so I think there are some other systems that have this the same problem as the motivation. So MATLAB is one of them. They also wanted to be kind of, you know, like linear algebra pseudocode that's executable. I think that was one of their motivations. I think, you know, Python has some of that motivation as well, you know, executable pseudocode also. Uh, I just don't think either of those languages did a very good job of it, clearly.
Makes
So
sense.
that's one thing. Let me see. And then
Um,
there's the other problem is kind of, I don't have a great name for it. Well, we talk a lot about the 2-language problem, which is like situations where you have to write a program in 2 languages. You know, like you do one part in C for speed and one part in Python. And it's fine to use multiple languages, but the point is you shouldn't have to, especially not for something as simple as just getting reasonable performance. Like that shouldn't be the reason you use multiple languages. So that's one problem we often talk about. But a little more broadly than that, I think there's also another problem that really interests me is the whole phenomenon of like numerical computing languages. So I think to a lot of people, they just think, oh, well, you know, there are lots of different languages for different niches. Different languages are good for different things. Numerical computing is one niche, so it has its niche languages. And I don't think that, I don't, that to me is not really satisfying. I don't think that's really true because it's not really a niche. I mean, because we're talking about like all of science, technical computing, data analysis. It's like, is that really a niche? Like, it's not really, it's almost, you know, everyone who does any kind of like scientific or analytical computing, which is a huge and growing population of programmers. You know, now this is, we're probably getting, if we're not already at the point where this is like the majority of programmers actually, because of the whole data science thing. And all of those programmers use a totally different universe of languages, like the MATLAB, Mathematica, R, like that whole, it's a whole different world of languages. And the programming languages people who know really knows a lot about programming languages hate those languages. They think they're terrible. They can't stand them, and they are terrible.
yeah, yeah, in fact, like I would say that the kinds of language design problems Jeff is dealing with Julia are just a different set of problems than people in traditional language design deal with. That's one of the reasons I thought it'd be really cool to bring Jeff on board because like every problem Jeff has described to me as needing to solve in language design, like just is out of scope of like what traditional like type theory or any of that does. And in fact, there was a dramatic situation where Jeff came to visit Carnegie Mellon during my first year there and gave a talk to the PL group. And I don't know, Jeff, if you want to characterize your version of it.
Well, I met some really nice people there. John Aldrich, is that right?
John Aldrich, yeah.
Yes, he was. Yeah, I had a great chat with him. He wanted to know about what we were doing. That was fun.
But I think that a lot of the like more traditional programming languages people, they're just like, but like what, like which underlying principles does this even relate to? And they're just like, surely this must relate to something. But it's just yeah.
Oh yeah, I can show you some stuff that'll make you furious. I can't wait.
Yeah, but I mean like pretty much everything. So there was a long period of time when I would have regular meetings with Jeff and the Julia crew because we were trying to write like a traditional programming languages paper. But the more I was like a therapist in that, like I would just ask them questions every week, like why is this like this? Why is this like that? And then what I deduced was did not have the skills and background to like turn this into the right paper. So, you know, I think you guys ended up working with Jan Tech at Northeastern.
Yeah,
but,
I didn't have those skills either, certainly.
Yeah, no, yeah, but it's just the kind, like, if you want to formalize the kind of things that people do every single day in numerical computing, in science, like non-niche things, as Jeff describes it, it's just very much outside of traditional programming language design, programming language theory, and all of that, which I'm really excited for Jeff to dig into, because it's like people, I feel like there's a lot of snobbery against like those languages designed for, you know, those purposes. But as Jeff says, it's like most of programming these days, and there's really like very little underlying, like there's no meta theory or anything for any of that stuff.
Yeah, like here's one. Like take here's something that bothers me. So say the computer science department at MIT, which I have some experience with. Everyone there.
Jeff and I are both PhD students there.
I did my master's as well, so have a little shared context.
So I took computer vision, for example, which was an awesome class. It was really, really fun, but it was all in MATLAB. Anyone there, and this is the CS department. It's not engineering or applied math. It's the CS department, but they're doing computer vision, machine learning, a few other areas. They used MATLAB, at least at that time they did. I think that now they probably do more Python, maybe some Julia if I'm lucky. But right, and like think about this. Like I find this unacceptable. Like talk about carrying coals to Newcastle, right? Like you shouldn't, MIT CS department shouldn't have to buy a horrible, slow programming language to do computer vision. Like this is nuts. Like how did this happen, right?
Yeah, one of my favorite things about Jeff is he makes these he's always made these very bold statements since like the first time I met him, and I really like he evangelized, like basically in the beginning it was just not MATLAB, and so I would just follow him around when he was my TA, just asking him for like more, like tell me more about why MATLAB is bad.
But it's not even, I mean, MATLAB isn't even that bad. Like it does some things pretty well. It's not that bad. It's more a question of why can't the MIT CS department provide a decent programming language that people like this want to use and that's effective? Like I consider that a problem. I mean, most people don't consider that a problem.
It's true.
But I do.
Yeah, so should we just get into the demo so you can show people the better way?
Yes, I think concrete examples are always the best.
Yeah. And
yeah,
I think,
of course, yeah.
Hong Yi had a question in the list of questions, which was like, why would someone want to pick up Julia today? What's that?
Oh yeah, I wanted to ask was like, you know, what do you think Julia is particularly like well suited for? Like, if I had a new project, why might I want to look at Julia versus other programming languages I might have available? So maybe you could give a demo of what one can do in Julia.
Yeah, so I'll show some specific examples. But I think it has one of the best combinations of performance and like elegance and simplicity that you can find. So if you look at graphs, when people do these comparisons of like performance versus lines of code, we're usually like out there on that Pareto frontier somewhere, or pretty close to it. So that's one of the big answers. You can just write something really simple, and that will compile to, you know, what you would want. That's the idea.
Yep.
And so there are a couple of things it's good at. I mean, if you're going to do any kind of program that needs to do any sort of math, simulations, differential equations, optimization problems, any kind of linear algebra, probably statistics, it's going to be very, very good. It has really good libraries for that and very good performance. And for some of those areas, actually the best libraries are the ones in Julia. So like for differential equations in particular, and the jump optimization solver stack. Those, maybe there's some others too, but those are definitely like, I think the best in class libraries for those things now. So those are a very big draw for a lot of users.
And like, Jeff, correct me if I'm wrong, but my understanding is the languages like R and MATLAB have really good built-in sub-procedures to make like certain things very fast. But Julia, for like anything outside of those, does a lot of like optimization and dynamic type dispatch, and a lot of really cool, really cutting edge performance things to make like any computation that you would want to write as fast as you can, as opposed to like, here's your catalog of a very small set of computations.
Yes, yeah. So one of our principles is definitely write everything in Julia. There's no like kernels written in C or something. You have to be able to write everything in Julia, and we optimize everything together. So this is, you know, that's really important, because like, for instance, we can, you know, if you want to solve a differential equation, you write your function or your derivative, and we inline it into the whole differential equation solver. So
yeah, it's totally nuts.
Those things.
Yeah, like it's like I think a lot of languages either give you flexibility or they give you performance. But Julia, like, it has such a nice optimization framework on top of flexibility, that like you can just write a lot of things in it. I'm not one of these scientific computing people, so like I personally can't like vouch for it on that level. But like from a language implementation point of view, it's super cool that way.
Yeah, and you know what, I like you know, to paraphrase Guy Steele, you know, we were trying to drag the MATLAB programmers halfway to Haskell.
Nice. But yeah,
I think that's one way you can look at it.
Yeah, but let's do some demos.
Okay,
I'll respond to some chats. There have been a lot of chats.
Let me share my window here.
Yeah, that's
all right.
Okay. All right. Do you have my terminal?
Yes,
yep,
we do. Let's look straight.
All right. Maybe a little bigger.
I think it's pretty good.
Is that good?
Yeah.
Okay. All right. So one thing about Julia is it has lots of data types. So I almost think of the phrase, this isn't a real term, but I don't know if it makes sense, but I almost think like if you have to pick like a paradigm, and I don't believe in paradigms, but there's this sort of, at times it's sort of like a data type oriented kind of idea, right? There's certain kinds of types in languages, like your numeric types, for instance, that have a certain character to them. They have sort of an unusually large and rich number of operations. And there's I don't want to get into that whole thing, but we have lots of data types. We have a huge number of numeric types. We have all kinds of structured matrices for linear algebra. There are units, colors, just so many of these things. So I'll show some of these. So one of the fun examples is units. So there's a package unitful, and we can also use there's this default symbols namespace that if you bring that in, then it defines things like, you know, then it defines things like 1m for meters, where, you know, you wouldn't normally want to bring just the single letter m into your namespace. So there's an extra step there. But so I can do 1 meter, 1 meter plus 2 meters, I get 3 meters. If I try to do 1 meter plus 2 seconds, that's an error. So that's actually a runtime error. I know some people might want a compile time error, but, you know, hold on, this is a runtime error. And you can do, you know, 1 meter times 2 seconds. And of course that works. You get meter seconds, or you can get, you know, 2 meters squared. And then Julia actually lets you introspect a lot of this. So like I can say, like, okay, what implements that? So I can say at which 1 meter times 2 meters, and it shows me which method. So we can see here it's a method of times of 2 abstract unit quantities, and it shows the source location that defines that. And you can also just say ask for the native code. So okay, what's the code for that? And that shows you basically that we generate essentially 1 multiply instruction for that. So what we use this sort of types here for is to basically pull that the metadata out of computations. That's sort of one of our major uses of the types here. But of course, all right, what if I do like a product of an array of meters? If they're 2, I get 2 meters squared. If they're 3, I get meters cubed. If they're 4, I get meters to the 4th, right? So like what is the type of that function, right? So yeah, it just works. It doesn't hassle you that this isn't, you know, type correct or something. It just does the operations, and
Wait, I have a
get the
dumb
answer.
question.
Mm-hmm.
So so when you call code native, that's actually you're looking at the compiled code. So like Julia is able to just sort of introspect on its own binaries.
Yeah, so we're compiling into memory, and in this case, we just disassembled it.
Okay, cool.
Yeah, using the LVM disassembler.
Yeah, Jeff, someone in the chat just said that's the lowest level someone has seen it be possible to dive in a REPL, which is cool.
Yeah.
Something I would also like to have you talk a little bit about, Jeff, is the like how the types in Julia work, because I think it's very cool. It's very different than how types would work in a Haskell-like language. But we've talked a lot about the philosophy of why Julia types work this way, like how people tend to program in science. And yeah, I'd love for you to just talk a little bit about that.
Yeah, so this is kind of an example right here, right? Is that we want the meters to be sort of a type. And so, okay, well, why might we want that? Well, it's basically because you can amortize that over an array, for instance. So like if I just print this array, we can see it says it's a 5-element array, and then it shows the element type of that array. And in this package, they have, I don't know, I don't fully understand this, but this is a Julia type. And they've sort of packed all of this information in here about like what kind of unit and dimension this is. So I know the L in there means it's a length dimension. And they just have, I'm not sure what it all is, but it's all information about what kind of unit this is, which is all it's put as part of this type. So for instance, that allows this array to have the same memory representation as just an array of normal ints, int64s. So it's very efficient because everything is the same type inside. But you can have it be heterogeneous. It doesn't have to be that way. You know, you can have different types in there as well. Like one of them could be meters squared. And now it's just the element type of the array is abstract, but it still works. So if you wanted to, so in some cases you could do a static analysis of these, and which we do. So we use extensive static analysis in the compiler to optimize programs. But of course, in general, it's undecidable. So you can't in general guarantee that you don't have certain type errors like that dimension mismatch error.
Yeah, and something else that I remember we used to talk a lot about, Jeff, is like on the one hand, you have languages that compile down to C subroutines, having like very fixed ways you do things, and things have to be just like one way. On the other hand, bless you or cough you. On the other hand, you have languages like MATLAB where it's so dynamic, you can do anything. But you had these stories of like MATLAB would just pick up your whole array and copy it if you were out of bounds or something like that. Where do you see Julia as falling between this? Is it like a series of like just good, clean design decisions that got you like in the sweet spot of this, or do you have a guiding principle for?
Yeah, that is a really, really important point of philosophy. So I think one kind of thing that's happened that's been suboptimal in the world is people have this, there's this sort of split between, you know, dynamic languages and static languages. And of course, dynamic language has no particular meaning, right? But in practice, it means just kind of anything goes, you know, anything can happen at any time. Someone else might change the value of one of your local variables, you know, the code of a method might change, you know, before you call it the next time, like, you know, anything can happen kind of a thing, right?
So you don't mean just like dynamically typed. You're using a more general term for dynamic language.
Yes, yes.
Okay.
So and so these are kind of our choices, right? You can have a kind of you can either have sort of everything statically checked, or you can have this kind of free for all, or sort of, you know, anything goes. And you know, those are certainly not the right trade-offs to have as the only available trade-offs. So yeah, so we in particular wanted dynamic typing because, you know, we thought there were certain useful things like this that you can do with types, but that you can't, you know, give people errors about these because you know, you can't say in advance what is right and wrong about ways to use these things. And there are many things that are just very complex, like the whole, so you can't even say like, you know, star given two things of the same type, returns something of that type, right? Because meters times meters gives meters squared, which is a different unit. So that doesn't fit the simple structure. It's not that you can't do it, but it's, you know, it's, and there, it gets even worse when you get into like, you know, structured matrices and the stuff that happens in linear algebra, where like the matrix structure might depend on the data that you have. And so there's lots of things like this happen. So it's very difficult to say like upfront, you know, which are the rules of what is and isn't allowed.
Awesome.
Well, should we progress the examples to something more out there?
Yeah.
Let's see.
Maybe something that, if you can think of an example, something that results in a poor outcome in a different language, but Julia does particularly well.
Well, I mean,
also, it's probably hard to come up with these slides, so I apologize.
Or Jeff, in the chat, Hillel is talking about how hard it is to statically type matrix operations. I know like Julia's matrix optimizations are like some of like the coolest things I've ever heard of, despite like, I don't work with matrices, so I don't actually hear about many of these, just like set a baseline here. But I know Julia, like you guys do some really cool stuff with matrices. So maybe we can, if you can show that off.
Yeah, so we have like all these matrix types, like, let's see if this works. So like I can make a diagonal matrix.
Whoa.
And so this is actually, so this is kind of cool because so inside we have this range type. So this is a, you know, a range, so it represents the vector of integers from 1 to 10, but it only stores the 2 endpoints. Pretty simple. But now we have this wrapped in a diagonal matrix type so that it will interpret this as a diagonal matrix. So this is a whole 10 by 10 diagonal matrix where the storage is just 2 integers, for example.
That's really cool. And I know you guys do all kinds of like both static and dynamic type analysis to like really optimize which sub procedures you use on your matrix computations.
Yeah, so like one example of where like this is really useful recently is in machine learning. They use these so-called like one-hot vectors, where it's 0 everywhere and 1 at one position. So obviously you can store that with just a single, you know, integer for which position has the 1, right? So that's what we do. And then having defined that, and so you can define these types really, really easily. That's kind of that's one of the big points. Like you can just write a couple of lines that say, okay, the representation is, you know, 2 integers, and here's how you implement, you know, indexing on it in just like 1 or 2 definitions, and then that's it. Then just everything just magically works. So like I can, you know, I can do, if I take a random 10 by 10 matrix, this should, so everything just sort of works magically.
Yeah, I know, that's amazing. And I know
I'd like to dig up the one hot vector example. Actually, I don't know if I can. Maybe can I find that, because it's actually a really good good example. I should have thought of that before, but
yeah, Hungy and I will stall until you find it. So, what does everybody think about the origin of the name Julia?
Who is right?
Yeah, there are some theories. We can scroll back up in the chat. So some people think that named after the Jane Fonda movie. Someone said it's named after the Julia e-cigarette. You know, there are a lot of conspiracy theories out there.
Wait, Julie? Oh, the Juul e-cigarette?
Oh, maybe that's what they meant. I don't know anything about e-cigarettes either.
I don't. Yeah, I've never heard of Julia cigarettes, but I've heard of Juul, the company.
Yeah, that's probably it.
Okay.
But,
well, Jean, one thing I'm curious about is, so earlier you were talking about how like the kinds of problems that Julia was trying to solve is out of the scope of what a lot of PL academics think about. And,
yeah.
is that? Yeah, I'm curious if.
Let me give some examples. Yeah, because like if you even look at this diagonal matrix type, right? Diagonal is a type that if it were a static type would be like a pretty hard, like these would be dependent types because they depend on the values itself, right? And so like correct me if I say the wrong thing about like what types of matrices are, but they're able to have types of matrices that are like upper diagonal, lower diagonal. They type like very specific properties of matrices that if you were to like do this as a static type, like that it would be really hard to determine. I believe the type can also change dynamically. Is that true, Jeff? Like something could be like a one kind of matrix, but it becomes another kind of matrix.
No, so the type a value cannot change type.
Okay, so that's at least good. But like a lot of these types are very data dependent, and like they're not even data dependent in a way, because like normally when you talk about a dependent type, like how you program with those are you have like this is an integer x such that only Alice or Bob can access x, or this is like an integer x such that x is always like greater than like 0 or less than 10 because it's some kind of bound. But like the kinds of types that you would have to statically capture Julia, like you could have like some machine learning operations, and if you run it on one data set or another kind of data set, you would imagine the type is actually quite different. And also like something interesting about the types for Julia is that they are for optimization, not for correctness. And so it is okay that you don't know what the type is before you run the program, if that makes sense. And so like those, in my opinion, are two of the key ways that like existing static types, like the in type theory, they're like for correctness reasons, and you kind of have to know what you're going for before you run the program. But for all of Julia's stuff, like you actually don't need them for correctness. It's really a performance thing, or it's either a performance thing or you like you know it after you see the data. You can't like it's really hard to just like come up with in your head like as a principle. And then it's also like it like performance is the main thing.
Yeah, no, that's all exactly right. Yeah. And, you know, there increasingly people want or wish they could have some sort of static checking. And there are things you can do. Like we should do more about using basically as a linter. Like we can get all this static analysis. We can't guarantee things, but we still have tons of information that we could show you potentially. So there's a lot more we can do with like linting.
And there's a question from the audience, Jeff. If you so in some languages you can table together an array and a matrix to get a tensor brick. Like how does that work in Julia?
I don't think I understand the question.
Like what happens if is it about combining an array and a matrix? I'll figure it out in the chat. But did we stall enough? Are you ready?
Oh yes, I'm in fact ready. Yeah.
Yeah.
So let's just define a new type of vector right now. So I'll just say struct one hot vector is a subtype of abstract vector with element type int. I'm just going to do int just to keep it simple. And we only need to know the index that has the 1 and the length. And so then we happen to need to define a method so we can get the size. So this means to extend the kind of base size function as opposed to like making a new local function called size. So this is now extending this. So we are actually, in some sense, mutating this function. So we are adding a method to this function that says, you know, the size of a one hot vector is a 1 element tuple of that length. That will do it. And then I just need to define indexing. So similar, but I define get index of one at vector, add an integer, and it's just we see if it's that index. So compare, get a Boolean, and convert that to int. And so that is actually all you need. So now I can construct one, say, let's do it index 3, length 10, and hey, look at that, it prints out. So just defining 2 methods, and then it sort of just inherits everything else that we know about, you know, any kind of array, and all sorts of things just start working, which is pretty cool. So like you can do, say, my diagonal matrix, or so I can multiply it by this other matrix. I could do.
Yeah, Hillel, is that starting to answer some of your questions?
I can multiply a random float matrix by it, and matrix multiply just works just from those 2 methods. So this is kind of the thing we try to make work. Like you can make a new kind of thing, and you just and lots of stuff just composes kind of automatically. And we can see if we look at what this calls. So this is going to call some just generic matrix multiply routine in this other, you know, in the standard linear algebra library that we have.
Have a lot of people written their own libraries and packages for, basically I'm asking how's the Julia ecosystem? Because I imagine, it sounds like there's a lot of functionality in the standard library, but also it looks like there's a bunch of other stuff out there because I saw you using a library earlier.
Yes, yeah, there are a lot of them. So you can actually go to juliahub.com and let's see what the current count is. Let's see here, packages. This is, okay, so as of now, there are 4,081 packages registered.
Nice.
So they're a fair number.
Yeah, I'm gonna go check and see what's on there.
You know, and I know it's not that many. I mean, people point out that like NPM has 900,000 packages and Python has 400,000 packages or something, but do you really need 100,000 libraries? I mean,
I was also gonna say NPM, like a lot of NPM libraries are like 2 lines. So,
right.
You know,
someone's inflating their numbers. You know, I'm sorry.
Yeah. So Jeff, something I'm super curious about is what was the timeline like on people starting to use Julia on like in large numbers, and like were they picking it up for things that you thought they would pick it up for?
Yeah. So like I said, it's been a kind of intentionally very slow process. We started working on it from nothing in about 2009, and then you know, Alan Edelman is great because I told him, I was like, you know, we're gonna spend several years on this. We're probably not gonna write any papers. I'm gonna be a pretty bad graduate student because this is gonna take quite a few years, you know, and he was okay with that. So, you know, you gotta respect that he was willing to do that. Not everyone is willing to take that kind of risk on us crazy folks.
Yeah, and also I'd just like to note that Jeff won like a departmental thesis award for Julia, and other people were like, well, you know, if you have like this many users, however many Julia had at the time, you can also win a departmental thesis award. And other people were like, this is not a fair comparison. But yeah, I think Jeff was an extremely good graduate student. I think a lot of advisors were like telling their students, if you're like Jeff, you too could have glory, and everyone's like, that's not a thing that we can reasonably do.
So we first released it in 2012 after about 3 years of work, and that's another one of the famous stories in the Julia lore is Stefan was writing this blog post to announce it. He came up with a great blog post, and Viral just sort of posted it to Reddit or something one day, and so he posted it once and nothing happened. And it's just like, I just fell off, you know, the page or whatever, and it's just absolutely nothing happened. I think a couple days later, he just tried posting it again. I think without telling us, he just did it. And the second time he tried posting it, somehow it took off and people noticed it, and it was like getting this massive amount of attention. And there's a great email where Stefan is like, Viral, we weren't done editing that yet. Why did you post that?
And also, I have to make this joke, but what you're saying is Viral went viral.
Yes, he's very well named.
Yeah. Also, yeah. Viral, for those who don't know, that's like how you spell his name.
Viral.
Cool. So, like, what did people? What were they excited about?
And I remember the first couple days were very intense because we had quickly started a mailing list, and there were lots and lots of people. I remember, I think within about a week, within 1 week, I think something like 80 people forked it on GitHub. So that was like roughly the order of magnitude. I happen to remember that number, I think.
I feel like that was a bigger deal back then.
Yes.
There weren't as many people on GitHub. Now, like, I don't know.
Yeah, we've been on GitHub for a long time. That was also Stefan's suggestion that we use that, which was also a good idea. So the order of magnitude was something like, you know, around 100-ish people within a week or two.
Yeah, that's cool.
And yeah, initially I think they were pretty much just the kind of people who we thought would like it. Like, you know, someone like Tim Holey, for instance, who does scientific imaging, and he does he's a neuroscientist, and he does like crazy, you know, 4D imaging where he like images high resolution 3D videos of neurons and brains and stuff, and then takes the time series. So he has these huge volume data sets that he wants to do crazy things to. So he needs a lot of performance. And he somehow saw this announcement. He has a story about what he was Googling for that led him to us. But, and so he found it and he's like, oh, I'll try this thing. And so he just downloaded it and, you know, tried porting some of his code, and he got like amazing speed, and he was just totally hooked.
Yo, Jeff, there's been a demo request. Automatic differentiation. Do you have one?
Okay, let me see if I can do it.
Yeah, we only have 10 more minutes, guys, so put in all your demo requests now.
Yeah.
I can probably do that. Yeah, let me just take a moment.
Yeah, I'm super impressed with Jeff's like on the off the cuff on demand demos. Wait.
Yeah, it's really tough on a live stream.
Okay, so let's see if I have. So I need Zygote. Let's just do the show off the package manager here. So in the REPL, you can type the closed square bracket, and it switches to a package manager prompt. The Julia REPL, by the way, is really excellent. I think it's kind of the best REPL out there. It's like you can do really cool stuff like full multi-line editing. You know, just move my cursor around, whatever.
Oh wow, that's awesome.
Such a nice REPL.
Yeah, very nice.
It has a shell mode, so if you hit semicolon, you get a shell prompt, and you can do like, you know, PWD, whatever. And then there's the package manager prompt. Oh, there's also a help prompt. So if you do question mark, you get a help prompt.
That's so fancy.
And I can say like, you know, sign, and it gets me help for a function. So it's really nice. We put a lot of love and care into this thing. So there's all kinds of goodies in the REPL. But yeah, so package manager prompt, and I will say add Zygote, because that's the kind of the leading auto diff package. I don't know if I have it in this environment, so just quickly try to fetch that. All right, yeah, it's downloading.
Really
stuff.
Smooth.
The package manager is also reproducible. So we have you can have an environment that's basically like with the directory you're working in, and there's what we call a manifest file that basically describes the full state of the full versions of absolutely everything you have. So you can just send that one file to someone, and they can just completely reproduce your environment of the same versions of everything. So that's really cool. But okay, so we'll do now using Zygote to load it. And now it's going to do this kind of compile thing. This is the thing Julia is slow at. So once we have stuff compiled, it runs fast. But we had kind of one of our biggest problems is compile time, actually, and the compiler performance, especially since we use JIT compiling. So we're kind of compiling things all the time. You know, like when I define that new type and I do operations on it, we're compiling, you know, new method specializations and all of that for all that stuff. So we're always compiling things. And there's a lot of, you know, so we have kind of similar problems like what happens in C++, doing template expansion. We generate a lot of code. We do a lot of compiling. It takes a bunch of time. This is something we've been really actively working on a lot.
Does it save your environment once you do that? Like, can I like somehow save my environment and later I can come back and have all the precompiled like type definitions, for example, that I had before?
So kind of. So we don't just automatically cache everything, but we do. So you can see it says here precompiling. So it is actually caching some of it. So it's not saving all of the native code actually, but it's saving basically all of its like parsed and lowered and type analyzed form of everything. So it saves some. It's able to save some of the work. There's another thing you can do, which we call building a system image, which is like kind of similar to like the Smalltalk system image concept, where you can just say, okay, everything that I have, just dump out all of that, and it'll write out a huge shared object, which you can then reload. But you have to ask for that specifically. But if you do that, then you get everything already compiled. And some people do that so that they can have a more responsive environment. So it's kind of possible, but it's not. We don't always do it automatically. That might happen soon, though. Okay, so yeah, so now I have a function called gradient, and I can just say, like, give me the gradient of x arrow x squared. So that's an anonymous function syntax. So square x, give me the gradient at 3. And then it has to think for a really long time. it's gonna think for a year and then produce 42.
While we're waiting, what were some of the like coolest or maybe most surprising uses of Julia that you found out about?
There we go. It gave 6.
Yeah.
But this is okay. This is even better though. I have a better I have a more fun demo of this. So I really like this. So we can let's make a dictionary. So here I made a functions dictionary where that maps a bunch of strings to functions. So sine becomes the sine function, cosine becomes the cosine function. And now I'm going to make a function that will read a line from the keyboard and then look up that function in that dictionary and call it on something. So we can just try that. Keyboard call of 1, and I can say sine, and it'll give me the sine of 1. Okay, and I can differentiate that. So I can say, give me the gradient of that. And I type in sine, and sure enough, that should be cosine. Yes. So you can differentiate a function that takes keyboard input and uses a dictionary.
Wow, that's incredible.
Cool.
Yeah.
Cool. So we only have a few minutes left. Do people have questions that they would really like Jeff to answer while we still have him? Someone wants to know if you bought a laptop now that you fixed time to first plot.
Oh, I did recently get a new laptop. Yeah. I was a little bit premature. I told everyone I wouldn't get a new laptop until I'd improved the latency, because I had a really old, slow laptop, so it was worse for me than for anyone else. But we're not done, so I kind of cheated a little, but I did recently get a new laptop. Yeah.
Yeah, Hongi had a question, I believe, that hanging.
Oh yeah, I was just asking what were some of the most surprising or I think coolest use cases that you sort of came across after you like through this process once you started releasing it and started seeing some real adoption?
Yeah, so there's a interesting company called Relational.ai that is writing basically a whole database and query engine that's oriented to machine learning, but the whole thing is done in Julia. And that's been really interesting because they have a lot of like really good database engineers who of course have always done like C++, of course. And and some of them were interested in Julia, some of them weren't sure it would work, but they're like fully all in on it, and they're writing the whole system in Julia.
Awesome.
Which is that's a really demanding application that's been kind of out there for us. And because actually one thing that Julia is really good at is if you want to make something kind of language like the DSL for optimization problems or a query compiler, for example, Julia is one of the easiest ways to basically construct at a high level like a symbolic expression and then get code generated for it. It is really, really easy because we just have eval, so you can just construct a function and call eval on it, and you'll get our compiler. So it's a really one of the easiest, closest hand ways to do something like that.
Cool. Well, since we are almost at the hour, Jeff, do you want to unshare your screen so everyone can see all of us again and we can say goodbye? Yeah, this was really awesome. It's been like I feel like I didn't know all these parts of the story. It was cool to see everything together. Yeah, so probably before we go, we should resolve the Julia name issue. We've left everybody hanging. The Julia name issue, Jeff. What is Julia named after?
Well, nobody really knows. It's a mystery.
I like that. I like that.
But I do like Julia Child stuffed mushrooms.
The mystery continues.
Conclude from that what you will.
Yeah, Jeff, is there anything that if people were going to go home and try Julia right now, you would tell them to try first? Or, are there any parting words you have?
yeah, try download it and use Zygote and try to differentiate things and see what breaks in file issues, because we're trying to make it work with everything. So it should be able to differentiate anything. So yeah, maybe try that. Try porting, your favorite program. I don't know. Porting something is always a good way to go.
Cool. And Hangi, how did you feel about your introduction to Julia?
Oh, it looks pretty interesting, actually. I do some like side projects in data science, and now I definitely want to check it out. So it's pretty exciting.
Oh, I didn't even get to the whole missing values thing, unfortunately.
Next time.
We don't have time.
Well,
well, up to you, Dean.
Yeah, that's true. Actually, I mean, I don't have anywhere to be. Well, all right.
Yeah, I have a few minutes.
Yeah, this is the official end of the live stream, but we're still streaming. We're gonna see the missing values thing. Goodbye, hello.
Yeah, this is also one of the most controversial things, so it makes it really fun. But just very quickly, I can do, for instance, this. So I can just start writing some like an integer, but also missing. We have this value missing that you can use for missing data, and that gives me an array whose element type is union of missing and int64. So you can do a proper lifted domain where we have a type that's all the int64s plus the missing value, which is a singleton. And this is not a tagged union. It's a set union. So it's an untagged union. So when I take an element out of this, that's just an int. So you don't have to unwrap it or anything. You don't have to unwrap it. You don't have to handle the cases. You just get whatever's in there out of it. And we store this efficiently, actually. So we will have each element will just be the size of whatever the biggest thing in the union is, and then we have an array of bytes at the end to keep the flags for what the types are of each thing. So to keep this efficient. So this is how we do this. And it's a pretty stylish way to do missing data.
That's really clean. That's so elegant.
Yeah.
Because it works for everything. You don't have to use nan. You don't have to use like the empty string. You can just use the missing value that you can union with any type.
That's amazing. I didn't know about that.
Yeah.
And the union thing is totally general. So you can do like, union of ints and floats. Like I can have let's say union int float 64. This should work. So yeah, it's got some ints, some floats, and you can union that. So
cool. That's awesome.
That's wild stuff. Just think about what that entails, right?
Yeah, that's so clean.
Yeah.
That's really cool.
Yeah, way better than nulls.
Yeah, this is really, really nice. Cool. Actually, there's one final question we should talk about. Someone wants to know how floating point not a number is handled.
How floating point nan?
Yeah.
Is handled? We follow the IEEE spec.
Cool. Awesome. Well, thanks, Jeff, for being on the stream. This was super cool. I don't know if you have time, Jeff, but I think people had some questions like in the stream. I don't know if you just want to scroll through, or if people want to ask your questions again to Jeff, you can like address them in the chat. But otherwise, this is the unofficial ending of our stream after the official ending. There's the secret missing numbers part. Someone said this all went over their head, but they're very grateful for your time, Jeff. Very good feedback in the chat. But yeah, Julia is a super cool language, and it's also been amazing to watch its evolution over the years. So I'm really excited that Jeff could be on with us today. And,
yeah, thank you so much for asking me to do this. That was fun. I don't often get to go into all these details, and yeah.
Yeah, no, that's awesome. And next week, Hangi and I will be going back to our roots. We're going to be picking a foundational paper to discuss. We still haven't picked the paper, so if you have requests, please make them to us in Twitter.
Yes.
Yeah, or other channels which you know how to contact us if you know us.
Or you can put it in the chat here.
Oh yeah, in the chat. That's
but
also
Twitter, but Twitter's probably more likely to be noticed. Like if you
yeah,
just
like
suddenly drop off.
if you put it in the chat right now, we'll look at it. But yeah, wait, actually, someone just said great to see me and Jeff together in the chat. I have to show everybody a picture. No, wait, I deleted the picture. I'm terrible. It's the worst. I'll put the picture in the chat too.
Have you talked about
Cusot and Cusot?
Right, we haven't. We referenced Cusot and Cusot. We haven't talked about Cusot and Cusot. We could do. I've been thinking about doing Cusot and Cusot.
Cusot, and Cusot.
Yeah, exactly. A lot of Cusots out there. It's like Yossarian. Yeah, there's just some guy named Cusot. Yeah, we could. That's definitely in the running. Yeah, actually, I should put my Taylor Swift papers thread because that's a good venue to choose off of. Cusot,
yeah, you could do that. You could run a survey or a poll as well if you wanted to, James.
Yeah, I tried to run a poll, but no one responded. Sometimes people don't respond to my polls, you know. But hold on, actually.
You invented the whole Taylor Swift as X genre, right?
I don't know if I invented it, but I feel like, you know, Taylor Swift as X really blew up this year. Who had a Taylor Swift as computers thread last year?
Because I'm pretty sure I saw it from you first, but
I also saw it from me first. I definitely didn't copy someone.
but the point is, it's catching on.
Yeah, it's really caught on. But here, let me just show you guys. Since we're really still in the unofficial part, we're still in the unofficial ending phase of the thing. But here's my Taylor Swift as papers thread. So we start out with
this is out there. Yeah.
Yeah, it's pretty out there. But yeah, so this is Taylor Swift as papers, and this one is the one that I start with the one that introduced for logic. So like how do we use preconditions and postconditions to like verify program properties. Then Cusot and Cusot, I was pretty proud of this one. So this is a paper.
This one is great. Yes, the lattice.
Yeah, Cusot 77 introduced lattices for abstract interpretation. So I'm really proud of like check out these lattices.
Oh yeah, this might actually be my favorite Taylor Swift as tweet so far. Actually.
Yeah, and then like we have the paper that introduced model checking. Like look at these models and what do they look like? Tassels, guys. And then yeah, the other ones are like not as visually exciting, but you know, like the first clue paper kind of has some like swirlies. Pierce Taylor with some swirlies. There's like the first proof carrying code paper. This is like one of my favorite papers of all time. But you know, you got like different lines of different sizes, and what do you have here? The paper that introduced I/O monads. That was also a big one. This like you know, back in the 90s, they used to format things like this. Taylor's dress. Typed assembly, also a big one. Yeah. But yeah, there's other big ones. But yeah, if people want to check out this thread and tell us which of these papers you want us to see cover. Like these are all like some of my favorites. There's like a couple, like you can't make these threads too long, so I have like 3 more favorite papers that I didn't put in there. But if you message me, I'll tell you what they are.
I like this suggestion in chat. Taylor Swift as SIMD instructions.
Oh yeah, there is a whole thread as Taylor Swift as SIMD instructions. Yeah, let me show you.
Wow. Oh,
so if we go to I know who did it. So it's someone so I have this Taylor Swift as textbooks thread, and then this Kate
I've seen a bunch of these. I haven't seen the SIMD one, I don't think.
Yeah, so this Kate person started responding to this one, but I have to find Kate. How? Show replies. Where's Kate? Show replies. Oh yeah, we'll just go to Kate directly. I think she's things Kate did.
Well, the 60 one is on point.
Oh yeah, no, I'm really proud of that thread too. But she got really into this thread, and so she did one of Taylor Swift as instructions. Oh, and then she also wrote some songs. Oh, this is also a good one she did. Programming Pro 2nd edition. Where is it? Somewhere. I don't know, guys. But yeah, it's somewhere in here. Somewhere on the internet. We'll find it. We'll put it in there. But yeah, if you guys have papers that you want me and Hongi to discuss next week. And Hongi, I don't know if you have like a type of paper you would like us to cover.
let me take a look at what the options are.
Yeah,
I have an idea.
but yeah, cool. That's what's gonna happen next week, guys. So it's gonna be fun. And I think that actually taking a classic paper and really reading on like both like what did it influence and like how is it still relevant today. So I also want to show you guys something else that's interesting. This is I feel like I once took this upper level literature seminar that was just like the leading world scholar on Homeric literature was just showing us YouTube videos like for hours every week. I feel like it's evolved into this, but let's see. There's something on my Twitter, which was developers. What's your number one source of truth for understanding what's going on with software? And something that I thought was interesting was so I have this theory that most people still see source code itself as the number one source of truth, right? And if we look at like all software analysis, it's you have like static analysis, like Husserl, it's all about static analysis, like the horologic stuff, all about static analysis. Everything that's been like trickling into popular mainstream programming is all about the source code. But like, I deeply do not believe that source code is the source of truth. And so like, I think there would be a really good dramatic discussion around like, what is the source of truth and like, how should we apply these like classic ideas to that? Because that's like what I spend 95% of my time thinking about these days.
Unfortunately, the source of truth for me is whatever I in my mind intended the program to do and perhaps was not able to articulate.
Yeah, the mind truth.
Person.
Yeah.
I feel exactly the same way.
That's my problem.
But yeah, cool. Well, on that note, this is PL Talk. It's weekly on Fridays at 3. We've just continued this discussion. We'll just be infinite Friday discussion from now on. But next week, yeah, we should be doing something fun if we get our act together. So.
Yep.
Yeah. Cool. Thank you, Jess.
Right.
And
Thanks
see
everyone.
everybody
Thanks, Jeff.
Sure. Thanks again.
Bye.
Bye.